Okay, hello Math 115 students. As I've mentioned, we'll be turning our attention to online learning for the time being. I'll be creating several YouTube videos going over these notes that I have posted to Blackboard, and so let's get right to it. We had left off in Chapter 4. We're in 4.4 and 4.5, and the fundamental theorem of algebra says that every polynomial of degree n has at least one complex zero and has at most n complex zeros. This theorem is basically saying that if you just simply look at the degree of the polynomial, you'll know right away how many zeros there are. Okay, so a degree 3 polynomial means that there'll be 3 zeros. A degree 4 polynomial means that there'll be 4 zeros, etc. Here's an example. So I want us to find the zeros of this polynomial. Now I've got a degree 3 polynomial, so I know right away that I'm going to have 3 zeros. And now in this problem, they're not giving me a k value. Some of the other problems that I had shown you were such that we were given a k value, and that was good because they were kind of helping us get started with the problem and giving us that number. Here they're not doing that. So unfortunately, to begin, I need to use guessing and checking. 0 is not a 0 of f because when I plug in 0, I get 4. 1 is also not a 0 because when I plug in 1, I get 1 minus 3 is negative 2 plus 4 is 2. That's not a... if we were to use negative 1, though, if we plug in negative 1 cubed is negative 1, minus 3 is negative 4, plus 4 is 0. And so, okay, negative 1 is going to be one of these 3 zeros. Now, I wouldn't want to continue guessing and checking because I have no idea what these other two numbers look like. They could be nasty numbers that I wouldn't even think of to guess and check on. Now remember, if k is a 0, x minus k is a factor. All right, so the plan here is going to be factoring f of x. Now I don't have a common factor. Factor by grouping won't work. And however, this is still going to be a factoring situation. Knowing that negative 1 is a 0 means that x minus negative 1 or x plus 1 would be a factor. To continue the problem then, I would want to divide f of x by x plus 1. So I'm using synthetic division here. Negative 1 is the 0 of the denominator. And the top row then in this chart is just simply picking off the coefficients that are in front of the terms that are in the numerator. I've got a 1 in front of x cubed, a negative 3 in front of x squared, a 0 in front of x, don't skip over that number, and then a 4 at the end. So when we divide then, bring the 1 down. 1 times negative 1 is negative 1. Add column 2, you get negative 4. Negative 4 times negative 1 is 4. Add column 3 and you get 4. 4 times negative 1 is negative 4, and when you add the last column, you get 0. And it's not surprising that we got 0 as the remainder because we already know that negative 1 is a 0 of f. Now, I'm more interested in what's to the left of 0, okay, because when I divide, I'm going to have 1 times x squared, or just x squared, minus 4 times x, plus 4 with a remainder of 0. In this equation here, if I then multiply both sides by x plus 1, then I'll have x cubed minus 3x squared plus 4 all alone on the left. Now that's what I'm calling f of x in the problem. And on the right, I've got x plus 1 times x squared minus 4x plus 4. Now you can see that I've already started to factor f of x. This guy here is going to factor further as x minus 2 times x minus 2. And now that I'm in a factored form, I can set the factors equal to 0, and I end up getting x equal negative 1 and x equal 2. However, x equal 2 has a multiplicity of 2 since its factor occurred twice. So the thing to see here is that I've got 3 zeros, not 2. Now all 3 of these numbers are complex numbers. Remember that a complex number is a number of the form a plus b times I. A and b can be any real numbers. That includes 0. So now these two didn't have an imaginary part. That's okay. We can still call those complex numbers. Okay, here's another example. I want to find the zeros for g of x. I know there's going to be 3 zeros. And this one here is going to factor by grouping. And if I let the first two terms be one group and the last two terms be another group, then x squared would be in common to these first two terms. You can factor that out, leaving you with 3x minus 1. We would need another 3x minus 1 coming from group 2, so if you pull out 9 from the last two terms, you'll end up getting that. 3x minus 1 is now in common to these two groups, so it can be factored out of the whole thing, leaving you with x squared plus 9 as the leftover. Set these expressions equal to 0 here, and you get x equal 1/3, and then x squared equal negative 9. When you take the square root of both sides, you'll have x equal plus or minus 3i. Okay, so I've got 3 zeros. I knew that before I did any calculations, because this is a degree 3 polynomial. All three of these numbers are complex numbers. Okay, 2 of them happen to involve an imaginary part, the other one doesn't. That's okay. All three of these are complex numbers. Notice how the way that we did this problem is different than the way that we did this other one here. Okay, I wouldn't want to use this particular method on the previous problem in the one here because, again, they don't give us a k value, and we would have to begin by guessing and checking, and it's not really likely that somebody would guess one of these three numbers. I know when I'm guessing and checking, I'm starting with like whole number values. I guess possibly 1/3 would be a number that maybe somebody would guess and check on. I'm definitely not considering imaginary numbers at all. But so the way that we did this problem was actually probably our best option rather than what we see here. Okay, think of this method as like a plan B option if you've ruled out the techniques that you've already learned when it comes to factoring. Okay, now the conjugate zeros theorem can be useful on occasion. It says if a plus b times I is a zero of a polynomial function, then its complex conjugate, a minus b times I, is also a zero. So just because 3i and negative 3i are zeros, that's not really any coincidence. Like those two numbers had to be there since those two numbers are conjugates of each other. Okay, here's another problem. I want to find the zeros of f of x. I know there's going to be 3 zeros. X is in common to all three of these terms, so you can factor out x and then set the expressions equal to 0. X equals 0 would be one answer. To get the other two, I would need to solve this quadratic equation, x squared minus 10x plus 29 equals 0. That's not going to factor nicely, so I'm using the quadratic formula. When you simplify, notice how we get 5 plus 2i and 5 minus 2i. That's no coincidence that those two numbers came up. It had to be that way since 5 plus 2i and 5 minus 2i are conjugates of each other. Okay, here's a problem. It says a polynomial function of degree 4 has zeros negative 7, 2/3, and 9 plus 13i. Find the remaining 0. Well, there's going to be 4 zeros, right? They gave me 3 of them. 9 plus 13i would be the conjugate of 9 minus 13i, so 9 plus 13i would be the answer. That's just a go right to the answer type situation. These other two zeros have nothing to do with getting the answer. We're just simply using the conjugate zeros theorem. Another theorem that can be helpful is called the rational zeros theorem. It says let f of x be a polynomial function. Here's the polynomial form that we've seen, where each coefficient is an integer and the first and last coefficients are not 0. If p divided by q, which is a fraction that has to be in lowest terms, is a rational zero of f, then p is a factor of a sub 0 and q is a factor of a sub n. Okay, now what we're doing here is we're going to create a list of possible zeros that are fractions. A rational zero is just a zero that would be in fractional form. And we're going to be drastically reducing the amount of guessing and checking if we are familiar with the rational zeros theorem. Here's an example of the rational zeros theorem. So suppose that I want to find the zeros of this function here. Okay, now I know there's going to be three numbers because I've got a degree 3 polynomial. I have no idea what these three numbers look like though. Okay, and guessing and checking could take some time, especially if the numbers are like, nasty numbers that I would never kind of think of to guess and check. So here's where the rational zeros theorem can be helpful. I'm identifying the p and q values. P is a factor of the last coefficient. Q is a factor of the first coefficient. So to get the p values, I'm just simply listing all the factors of -6. 1 is a factor of any number along with -1. 2 goes into -6 along with -2. And by the way, if a number is a factor, its opposite is going to be there. So I'm going to have plus minus for all this stuff here. 3 goes into -6 along with -3. And then 6 goes into -6. -6 is also a factor of itself. And so in all we have, it looks like 8 numbers that are factors of -6. Now do the same thing with getting the factors of 2. 1 and -1 go into any number. 2 is a factor of itself along with -2. And so there are 4 factors that go into 2 evenly. Okay, now that I've identified the p and q values, I want to list all the rational zeros of f. So I'm going to start by listing all the numbers where 1 or -1 happens to be in the denominator. If you take plus or minus 1 over plus or minus 1, that's plus or minus 1. Plus or minus 2 over plus or minus 1, that's plus or minus 2. Plus or minus 3 over plus or minus 1, that's plus or minus 3. And plus or minus 6 over plus or minus 1, that's plus or minus 6. And now move on to if 2 or -2 happens to be in the denominator. Plus or minus 1 over plus or minus 2 is plus or minus 1/2. Plus or minus 2 over plus or minus 2 is plus or minus 1. I've already got 1 and -1 both listed, so I don't need to list those again. Go on to the next number here. Plus or minus 3 over plus or minus 2 is plus or minus 3/2. And then plus or minus 6 over plus or minus 2 is plus or minus 3. I've already got 3 and -3 both listed, and so I don't need to list those again. So it looks like in this problem, I'm going to use guessing and checking, but it would make the most sense to be guessing and checking only this list of 12 numbers, because the theorem says that if the zero is a fraction, it's going to be one of them listed. Okay? So now I can begin my guessing and checking. Like if I'm using 5, I'm wasting my time because 5 did not come up in this list. So I'm starting with 1. Okay, 1 is not a 0, since when you plug in 1 into f, you get -12. -1 is also not a 0, since you'll get 6 when you plug in that number. But if I plug in 2 into the function, I end up getting 0. Now I suppose that I could continue guessing and checking. However, that wouldn't be a recommended option because, again, we don't know what these other two numbers look like. They could be nasty numbers, and we would have wasted our time then in just guessing and checking and gotten nowhere. Knowing that 2 is a 0 means that x minus 2 is a factor, so we'd want to plan to finish up this problem by factoring. I'm dividing here, and you can use synthetic division. 2 is a 0 of the denominator, so I've got my chart set up here. Of course, these are the coefficients from the numerator on the top row. Bring the 2 down. 2 times 2 is 4. Add column 2, you get 7. 7 times 2 is 14. Add the next column, you get 3. 3 times 2 is 6. Add the last column, you get 0. That looks good. We already know that 2 is a 0, so we should have expected to get 0 left over in the remainder in dividing here. And as an expression involving x, we end up getting 2x squared plus 7x plus 3 when we are dividing these two. In this equation, multiply both sides by x minus 2, and you can factor 2x squared plus 7x plus 3 further. Here's how that would factor. And now that I'm in a complete factored form, I can set these factors equal to 0, and I get x equal 2, x equal -1/2, and x equal -3 as the three zeros. Now notice how those three numbers are actually listed in this group here. So I guess in this problem, if I would have guessed and checked, like I could have found those numbers. But again, that's not a great strategy in general because the theorem says that if the numbers are fractions, it's going to be listed. We don't know if the numbers are not fractions, if they're If they're like square roots or imaginary numbers, then they're not going to be on the list. So guessing and checking really isn't just a go-to thing. We'd really want to use this factoring approach here. Okay. Here's the homework problems for section 4.4 and 4.5. Be sure to look at those for me, and we'll stop right there.